Welcome back. It is Latin Square time. We are going to be working through Lab 5 Example 2. This is a simple Latin square, a 4x4 Latin square, and it is unreplicated. In other words, we have just a single square to deal with. This would be the simplest case. And in this particular example, we're going to look at the ANOVA, and again, like we did with the RCBD above, we're going to walk through what assumption testing looks like for a Latin square. So let's do it. I've already loaded in the script. This is Lab 5 Example 2, the R script, and I've loaded in the accompanying data set, naming it ls.dat because that's what I refer to it as in the script. So as before, once everything is in, you want to look at the structure of that data set, and it is interpreting treatment with levels A, B, C, and D as a factor. That's great, but it's also seeing my row and column. These are my two generic blocking variables. It's interpreting my row and my column as integers instead of factors. So we need to fix that. That's what's happening in line 8 and 9 here. We are reassigning row, reclassifying it as a factor, reclassifying column as a factor, and taking a look again at the structure of the data set. Now all three classification variables are factors, and I have my response variable. And due to this very significant constraint of a Latin square, of course, the number of factors of my first blocking variable, my second blocking variable, and my treatment are all the same. And in this case, they are all 4. So this is a 4x4 Latin square that we're dealing with. As with the RCBD example above, you would start off by running the appropriate ANOVA. In this case, the linear model is that my response is explained by the 3 classification variables in my model. Blocking variable 1, which is my row, blocking variable 2, which is my column, and treatment. Again, row and column are here and present in my model simply because I'm trying to control error. It is really just the levels of treatment that I'm interested in terms of hypothesis testing. So treatment is a fixed effect, row and column are random effects, and they are there simply for error control. But that is my model. As we did with the RCBD above, what would happen if I put the interaction between one of the blocking variables and treatment in the model? If you do that, you see that my row, column, and treatment each have 3 degrees of freedom because they each have 4 levels. If I put any interaction between them, it costs me some degrees of freedom, and it costs me more degrees of freedom than I have available. It bottoms out the residuals that I have. So this is why none of the block treatment interactions nor the block interaction are included in my model because we don't have the degrees of freedom for it. But if you take it out and run it appropriately, you get an ANOVA table with 3 rows in it relative to the model. These are my 3 classification variables: sums of squares, mean squares, and F tests related to each. And you also have residuals, of course. This is my experimental error. And in this particular case, my experimental error is actually comprised of all these interactions that we're talking about. Because we don't have true replication in the experiment, as within the RCBD with 1 experimental unit per treatment block combination, here we don't have true replication either. And so we are approximating our experimental error through the interaction terms, and that's what we have down here. So we run this initial ANOVA, and as before, we don't really pay much attention to the result here because first we need to make sure that we have met all the assumptions. As with RCBD, what we want to do is grab my residual and predicted values. We also need to run these 1 degree of freedom Tukey tests, but you'll notice that I don't have the squared predicted values here. The reason for that is because we have 3 classification variables, we actually have 3 different interactions that we need to test, and each one of those we need to compute the predicted squared values separately. But for normality and a homogeneous variance, we grab the residual and predicted values as we did above. We can take a look at our data set, head ls.dat, and you'll see that they pop up here. We have our 3 classification variables, our response variable, and now we have a residual and a predicted column. With those residual and predicted values, we can create a scatter plot. These are the tea leaves of our experiment. You know, this is not as amorphous as I would like. It looks a little bit like it's smiling at me. It looks like we have a bit of a bigger scatter up here at higher values than at lower values. And so it looks like a pattern that we don't want to see is maybe beginning to emerge in our data here. So we're really going to want to take a look at our assumptions tests to make sure that our error in our model is behaving as it should, as we need it to for an analysis of variance. So we jump into that. First thing we would do is run the test for normality, and that is, again, a Shapiro test on the residuals. We actually see that we are very, very good in terms of that test. We fail to reject the null hypothesis, and so we would conclude that these, the error or the residuals in our model were sampled from a population that was in fact normally distributed. Next thing we're going to want to do is run a Levene's test specifically on treatment, because it is the levels of treatment that we're going to be forming hypotheses about and making conclusions about. So we need to make sure that the error term that we're using is appropriate for all the different levels of treatment. That's just the Levene test within the CAR package. And as before with the RCBD, even though the true Latin square model has 3 classification variables, when you run this Levene test, you reduce it to a one-way ANOVA response as explained by the thing that you are probing for homogeneous variances. Run that, and we see that we're actually looking fairly good there as well. So the pattern that maybe my eye was picking up here at least does not bear out statistically. It seems that we're quite fine. Now, for testing for non-additivity, let's go down a little bit. Come down here to line 41. Here I have 5 lines of code, the whole purpose of which is to test for the significance of the row treatment interaction. Remember, row is a blocking variable, treatment is my treatment variable. So what I'm doing is probing for the significance of this block treatment interaction. I am probing for any non-additivity in the model. I want to make sure that row is behaving as a blocking variable should. In order to do this, in order to run the 1 degree of freedom 2-key test in this particular case, what you do is you run a slightly reduced model that includes only the 2 variables that you're probing the non-additivity for. So I'm running a linear model. I'm calling this Latin Square RT, row treatment. This is my Latin Square row treatment model, in which response is explained by row and treatment. I grab the predicted values from that model, I square them, and then I rerun the model, tacking on the squared predicted values as a regression variable. So this is exactly what we saw in the RCBD case above. If you do all that, I'm going to run these 5 lines of code. You pop out with an ANOVA table, the only purpose of which is the p-value right here associated with that probing of the quadratic component. And here we see non-significance. So we fail to reject the null hypothesis. It looks as though we the effects of row and treatment are additive. There are no non-additive effects. So row is behaving as a good blocking variable. We'll do the same thing with column and treatment. Remember, we have another blocking variable in this case. So we run an LS column treatment model with only those 2 classification variables, column and treatment. Grab the predicted values, square them, tack on those squared predicted values as a regression variable in the model, and run those 5 lines of code. And again, we have non-significance. So column looks like it's also behaving as a good blocking variable. And then, of course, the third thing you want to look at is the block-block interaction. Here I have an LS row column interaction. This is line 34 of the script. Predicted, squared predicted, tacked on as a regression variable. I run those 5 lines of code, and I also see non-significance, a very low p-value. So for this particular data set, we have met the assumption of normality, we've met the assumption of homogeneous variance, and it looks like all of the blocking factors are behaving additively. They are behaving as blocking factors should. So we can use them as error control in our model without without losing sleep over the fact or of the idea that maybe we don't understand our system very well, or that we need to characterize these blocking variables in some other way. Moving on down, once all those assumptions are met, as I say here, you feel free to continue the analysis as you see fit. That could mean, depending on the treatment structure, it could mean just a mean separation table. It could mean a bunch of contrasts if these were planned questions motivated by the treatment structure. And I show you the code that you could use in each of those cases, but it'll look very similar to code you've seen in previous labs. With that, I think we'll move on to the last video in which we look at the case of replicated Latin square. Before we move on to that, though, let me bring your attention real quick back to the ANOVA table. Let's go back up in our script and pull up that ANOVA table again. That's from the very beginning. When you run this ANOVA table, what we see is that rho was non-significant. What that's telling us is that there really do not appear to be significant differences between the levels of that blocking variable. And that should cause you to wonder whether or not it was worth blocking by rho. And this is a relevant question because blocking by rho not only cost you 3 degrees of freedom, but it also forced you into a very constrained experimental design, this Latin square in which row and column and treatment levels all had to be equal. If there really was no benefit in terms of error control of blocking by rho, it's possible that you were penalized here. And as I mentioned on page 10 of the lab handout, the best way to ask this is to look at the relative efficiency of the two experiments. The one experiment being the Latin square that you ran, and the other experiment being a hypothetical RCBD in which the column factor was the only blocking variable. And so you would have to ask about this relative efficiency question, and what you may find is that you in fact didn't gain anything. You may have even lost something by blocking by rho, and if you were to run this experiment again, don't block by rho, simply block by column and free up some of the constraints of your experimental design, and you would likely be better off. Okay. Onward and upward.